The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. You know, the legendary physicist Richard Feynman said that, and honestly, it perfectly sets the stage for our explainer today. Because the story of how we figured out the nature of light, it isn't just some boring timeline of facts, it's really the ultimate historical detective story. It's a story entirely driven by that exact scientific test, literally centuries of guessing, observing, and absolutely crucial to everything, experimenting.
So welcome. Today we're going on a pretty thrilling journey, from the really early philosophical guesses of our ancestors all the way to the modern technological marvels that, well, power our world today. We're going to explore the fascinating history of optics.
Okay, let's dive into this roadmap. We'll be navigating through 5 key eras: the ancient observers, the medieval optical revolution, lenses and telescopes, the wave versus corpuscular showdown, and finally, the modern optics era.
Let's start right at the very beginning and turn the clock back a few thousand years for Section 1, the ancient observers. Picture this. It's around 400 BC, and the Greek philosopher Arcadus genuinely believed vision worked like a pair of invisible flashlights. Seriously. He thought we shot fire directly out of our eyes to reveal shapes and colors. And while great minds like Euclid and Ptolemy made fantastic strides, mapping out the geometry of straight lines, reflection, and even measuring refraction in water, they kind of couldn't shake that eye fire myth. But jump to the 5th century, and the brilliant Indian mathematician Aryabhata hits the nail on the head. He correctly challenged the myth, pointing out that light actually arrives from an external source to illuminate the world, rather than, shooting out of our retinas.
That foundational geometry perfectly tees up our next major leap forward in Section 2, the medieval optical revolution.
Enter the sheer, undeniable genius of Ibn al-Haytham, or Alhazen as he's widely known today. He is basically the true father of optics. In his massive 7-volume book of optics, Alhazen completely busted those ancient misconceptions from Euclid and Ptolemy. Through really rigorous experimental study, stuff with pinholes and reverse images, he proved definitively that light is made of rays originating in the object you're looking at, not the eye. He even stated that light takes the easiest and quickest path through a medium, which, if you know your physics, anticipates Fermat's principle of least time by many, many centuries. It's an absolute mind-blowing historical Easter egg.
And science is all about standing on the shoulders of giants, right? Over the next couple of centuries, Alhazen's rigorous work crossed borders and profoundly influenced Western thought. In the 13th century, the Polish scientist Witello directly relied on Alhazen's groundbreaking discoveries to write his own massive 10-volume masterpiece called Perspectiva. And that text served as the absolute gold standard on the subject all the way until the 17th century.
With that theoretical groundwork firmly laid, humanity started actually physically manipulating light. Which brings us to Section 3, lenses and telescopes.
So although Alhazen studied reverse images way earlier, it was the legendary polymath Leonardo da Vinci who gave us the first really detailed description of the pinhole camera, the camera obscura, around 1485 in his Codex Atlanticus. He brilliantly used it to study perspective, completely blending his artistic mastery with the physics of light propagation.
Jump forward a little over a century, and a towering figure steps onto our timeline, Johannes Kepler. In 1604, Kepler published a book that, well, it didn't just tweak existing knowledge. It completely reconstructed the theory of light, the complex physiology of vision, and the mathematics of refraction. It was just a massive paradigm shift that finally gave astronomical optics a solid, mathematically rigorous foundation.
Now, what's really interesting about this is how that mathematical foundation paved the way for Galileo Galilei, a man rightfully called the father of modern physics. In 1609, he was inspired by the playthings of Dutch eyeglass makers, folks like Hans Lippershey, and Galileo utilized those lenses to pioneer the first astronomical telescopes. He pointed them up to the sky, observed stars and planets, and fundamentally changed our understanding of humanity's place in the universe. And shortly after that, he pioneered the compound microscope to look in the exact opposite direction, at the incredibly small.
But here's the thing. To truly master these powerful new tools, scientists had to mathematically master refraction. Now, refraction is just the bending of light rays as they pass from one medium to another. Think of how a straw looks broken when you stick it into a glass of water. Its fundamental mathematical law was discovered by the Dutch astronomer Willebrord Snell van Rooyen in 1621, which is why we call it Snell's law today. This precise understanding was the absolute key to unlocking modern optical instruments.
But even as our telescopes were getting better and better, a huge fundamental question remained entirely unanswered. Section 4. Wave versus corpuscular models. What actually is light made of? Before we can answer that, we've got to introduce a strange new phenomenon, diffraction. Discovered and named by Francesco Grimaldi around 1660, diffraction literally means the breaking up of light from a straight path. Imagine how totally bizarre this must have seemed back then. Grimaldi noticed light entering a shadow and acting almost like a fluid in a state of constant vibration. This weird observation is actually what directly inspired a young Isaac Newton to start studying optics.
And that led to the ultimate scientific showdown of the 17th and 18th centuries. In one corner, we had the corpuscular model, championed by René Descartes and heavily pushed by Isaac Newton. This model argued that light is just a swarm of tiny spherical particles, or corpuscles. In the opposite corner was the wave model, proposed by Christian Huygens and later Thomas Young, arguing that light actually travels through space as interfering waves.
Let's see how this builds, because the discoveries start coming at a breakneck pace. In 1638, Descartes pushes the particle theory. By 1660, Grimaldi's diffraction hints at waves. Then in 1676, the Danish astronomer Romer makes the very first quantitative measurements of the speed of light, which is incredible. And just 2 years later, in 1678, Huygens formally pitches his wave theory to the Académie des Sciences in Paris.
So, who ultimately won the big debate? Well, in 1801, the English scientist Thomas Young performed an incredibly elegant two-hole interference experiment. By showing that light shining through two tiny holes creates a distinct interference pattern, literally exactly like ripples interacting in a pond, he beautifully and undeniably demonstrated the wave nature of light. He even used this wave theory to explain the shifting colors you see in thin films, like soap bubbles. Honestly, today, it's still considered one of the most beautiful experiments in all of physics.
All of this intense theoretical detective work over the centuries eventually birthed the tangible world we live in right now. Let's look at Section 5, the modern optics era. Because this isn't just abstract physics. This is the literal fabric of our modern lives. Starting with the first laser back in 1960, we've seen an absolute renaissance in the field. I'm talking about the fiber optic communications that power the entire global internet, holography, DVD technology, and even mind-bending stuff like supercontinuum generation, where laser pulses generate entirely new frequencies. So the crucial point is that those ancient philosophical arguments about eye fire pave the exact path that allows you to stream this very explainer over fiber optic internet today.
Which brings us to a rather profound thought to end on. We've gone from ancient Greek philosophers guessing about invisible eye fires to firing incredibly precise lasers and manipulating the quantum mechanics of a single photon. So I'll leave you with this. What revolution in light is waiting just around the corner? Thank you so much for joining me on this explainer. Keep questioning and keep looking closely at the world around you.